Hello everyone, welcome to Lecture 7 entitled Variability. Lecture 6 was all about central tendency and finding out where most of the numbers in the distribution of scores lied. Lecture 7 isn't about that in any meaningful way. It's really about figuring out how far apart all the scores are. So for Lecture 6 we were trying to figure out sort of where's the middle. Now we're trying to figure out the spread of a set of scores. And so hopefully at the end of this lecture you'll know everything there is to know about variability, or at least what you need to know to pass this course. So let's jump right into it. The learning outcomes for this lecture are for you to, one, understand the purpose of measuring variability. So we're going to have you define range and compute range, and there's three sort of versions of it. You can get the range, you can get the semi-interquartile range, and you can get the interquartile range. So we'll learn what all those things are. Don't even worry about it now, I'll show you later. 4 is the most important one. I want you to understand variance and standard deviation. And I want you to understand these terms at a very deep level, okay? This is not something you just sort of need to like read off the page and put in your brain just so you can spit it out. You need to understand these things conceptually because they really do form the basis for everything else that we're going to be doing in the rest of this course and pretty much the rest of your life if you go on to do any more statistics other than this course. So these are very important concepts that I'm going to spend a lot of time on today, and I'm spending a lot of time on them because they're very important for you to learn. And it's not just important that you learn how to calculate them, right? So we'll learn how to calculate them for the population and a sample because the formulas are a little different. And so there's 8 of them that you have to learn over the course of this lecture, and 8 formulas for these things. And really, if you just know one of them, you'll be good to go. And I'll show you how. Let's do it. In terms of the tools that you'll need for this lecture, you need to know everything about summation notation, which was way back in chapter 3. And you also need to understand central tendency, which we covered last time. And the central tendency measures that you really need to understand very well for this lecture are the mean and the median. So when we want to talk about a distribution, right? Before we even talk about variability, let's think about things that we need to talk about when we're characterizing a distribution. If I gave you a set of scores that were, let's say, the final scores for the course for last year's class who took this course, right? I could give you that distribution of scores and just show you what all those numbers are and ask you to summarize it. And if I asked you to summarize it, there's sort of 4 characteristics about that distribution if you graphed it that we would notice, right? One of them would be central tendency, right? So you could describe that, distribution to me in terms of the mean, median, and the mode of that distribution. However, you could also talk about it in terms of its skewness. And so we learned a lot about skewness last time, right? And how it affects the distribution. So skewness refers to whether it's symmetrical or not. And if you have one high score that sort of is an outlier, right? We know based on last lectures that would essentially pull the mean up higher than it should be, right? And so the mean would be higher than the median, which would be higher than the mode. And if you had a negatively skewed distribution, the opposite would happen, right? You'd have this one low score that's pulling the mean down. And so then the mean would be lower than the median, which would be lower than the mode for that particular distribution. So that's what skewness is all about. Kurtosis is one that we don't really pay a lot of attention to in this course. It's not important for the types of analyses we're going to do, but it refers to whether it's a tall, pointy distribution or a short, sort of squat distribution. And then finally, we get to variability. And variability is all about how spread out is the distribution. How wide is it or how narrow is it? Okay? Cool. So, variability can be defined in several ways, okay? It can be described as the quantitative distance measured. It's based on differences between scores, and it describes the distance or spread of scores or distance of a score from the mean. And so variability really is about how far on average things are from the mean. The reasons why we are interested in variability or indexing variability in different ways primarily are because we want to describe the distribution, right? We want to describe or get some idea of whether it's a clustered distribution, so whether all these scores are sort of tightly grouped, or whether it's not very tightly grouped and is pretty much spread out. And we want to do this because we want to measure how well an individual score represents the distribution. So again, we got that central tendency measure, right? We said that's the mean. Well, the mean is probably a much better representation of all of the numbers in a distribution if it's a nice tight cluster of scores. But if the scores range from 1 1 to 1,000, right, that mean doesn't do a good job for any number, right? And so we have to sort of balance the nature of the mean with the variability of the distribution to find out, is it actually a good indication of where any score should lie? And it's always going to be the case that distributions with less variability, the measures of central tendency are better for those than they are for ones that are wider, simply because there's less spread there, okay? So let's look at the distributions of height and weight in the American population. So we got height over here on the left under A, and we have weight over here under B. And you'll notice, first of all, that the distribution for height is skinnier, right? So for height, this thing is skinnier than this one, right? And so what that means is that this one has less variability. There are more people who are more similar here than there are over here, right? So you're going to see a wider range of skinny to overweight people than you are of tall to short people, right? You're going to find some really, really, really skinny people. You're going to find some really, 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 really not skinny people on the other far end of the distribution, okay? And the range of people that you'll see in terms of being skinny to not skinny is different from short to very tall, okay? That seems pretty straightforward, just sort of looking at that picture. So variability in terms of a strict definition, it's a quantitative measure of the degree to which scores in a distribution are spread out or clustered together. And there's sort of 4 ways that we sort of define it in this course. The first one is sort of the easiest one, that is the range. The second one is pretty much just as easy. It's the interquartile range and the semi-interquartile range. And we don't really use those too much. We have ones that we prefer. We prefer variance and standard deviation, whereas variance is just a number. The square root of the variance is the standard deviation. So I'm going to show you how we calculate both of those in a second. So let's talk about the range first, though, okay? So again, the range basically tells us the distance covered by the scores in a distribution. It's a very simple formula. Let's do it. So basically, we have to find the smallest value in our data set, and we find the largest value in our data set. And for continuous data, we can use the row limits, or there's an alternative way to do it. But essentially, there's 2 ways to calculate the range. You can get the upper row limit for the highest score, and you can subtract from that the lower real limit for the lowest score. Okay, that way you're covering all the possible bases, and that's one way to calculate the range. An easier way that most students prefer, and probably the one that I suggest so you don't make any mistakes about it, you could just take the highest score and then subtract the lowest score from it, and then add 1 to whatever that number is that you end up with. That way you don't make mistakes with your intervals and mess up something along the way. So let's go ahead and do a couple of these, right? Let's find the range of this set of scores, okay? And we're going to use the second formula because that's easier to do. So the second one, if we say the largest number is 9 and the smallest number is 3, right? So what would the range be for that? You guys got it. So it should be 9 minus 3 equals 6 plus 1 equals 7. Easy enough. So let's do a second example now. So we have this second set of scores, right? And so let's pop our calculator up because it's got some weird things here. So we need to do 20 minus 4, and then we'll hit the negative sign for that. And so that gives us 24. And then we need to add 1 to that. So plus 1 should equal 25. And so the range for this set of scores should be 25. Easy peasy, right? Calculating the range is one of the simplest things that you have to do. So high score minus low score plus 1 gives you what the range is. Now, the range has a couple of problems as a measure of variability, and one of them should be blatantly obvious to you given what we learned last time. The first problem with the range is it's based only on 2 scores, right? And so it's not based on all of the data, it's only based on those 2 scores. And because of that, the biggest problem with it is it's an imprecise measure because like the mean, it ends up being heavily influenced by what? Outliers. There you go. And so we don't like the range when we have good scientific data. It just doesn't really tell us a whole lot compared to these other measures that we'll talk about shortly. And additionally, the sample range, it tends to underestimate the population range. So that means if we take any sample, right, and we try to say, hey, here's a sample out of the population, it's always going to be lower than what the actual range is for the population, unless you happen to randomly get the highest person and the lowest person. But what are the odds of that happening, right? So pretty much any sample range will pretty much always underestimate the population range. And therefore, it's not really good for statistical purposes because you can't draw inferences about that in the population. And that's bad because that's exactly what we want to get to be able to do. So we don't tend to like the range for that particular reason. So we say, okay, well, if we're worried about those scores that are on the end, maybe we should just sort of leave those guys out and sort of think about ones that aren't so far out. That way, if the, range is biased because we have these outliers. Okay, well, let's think about another way we could do it. We could get the interquartile range and the semi-interquartile range and try those guys and see what they come up with. So quartiles, and if you guys remember this from an earlier lecture where we did it, frequency distributions, a quartile refers to dividing the scores in a distribution into 4 parts, okay? The first quartile is defined by the first 25% of the scores in the distribution. The second quartile is the middle of the distribution, so that's the 50th percentile, right in the middle. This third quartile, Q3, equals the 75th percentile. And finally, everybody's in Q4 because that's everybody, right, in the 100th percentile. And so we can take those things and we can actually find what those are, right? You guys did this already with the frequency distribution table stuff that we did in earlier lectures. If you do that, you could figure out what score is at the 50th percentile, the 75th percentile, the 25th percentile, and so forth and so on. And you could calculate the interquartile range. And so what the interquartile range is, it's basically Q3 minus Q1 for whatever that data set is, for whatever you determined it to be. And if you can calculate the interquartile range, the semi-interquartile range, which we call SIR, is basically the exact same thing except divided by 2. And I have no idea why we do that, but we just do because we do a lot of weird things in psychology, and it doesn't matter that much anyway because we seldom use the interquartile ranges for anything short of teaching students what they are. So let's go ahead and try to compute these things, okay? So one of the things that I could do if I was feeling particularly evil for a test is I could just give you a set of scores. And I could say, hey, what I want you guys to do is compute a frequency distribution table, so build that thing out, and you guys already know how to do that. So if I gave you the set of scores, you would basically get the frequencies of each one, you'd have to get the cumulative frequencies and the cumulative percentages, right? And then I could say, okay, now solve the range, the interquartile range, and the semi-interquartile range. Well, the range is fairly simple, right? It's basically going to be the top number minus the bottom number plus 1. But to get these guys, you have to figure out where Q3 and Q1 is. And it just so happens that in this data set, because I was kind, guess what I did? I gave you all of them where these numbers just happen to magically show up in your cumulative frequencies. That's not always going to happen. So if I was going to be truly evil, I could just give you something where you have to figure out what score is at the 75th percentile, then you have to figure out what score is at the 25th percentile, and then together you have to take those numbers and then do it all over again to figure out what score, what those differences are. So you have to solve for them, but instead here I just give them to you, so you don't really have to do any extra math to find that out after you've done all of this math. Okay, so Q1 is at right there, so Q1 is the 25th percentile, and that's a score of basically 10.5. Q2 is at the 50th percentile, Q3 is at the 75th percentile, and finally Q4 is all the way up there. So if we're going to calculate the range, again, I said this earlier, but the range would essentially be 16 minus 8 plus 1, right? Because it's the highest number minus the lower number plus 1. The interquartile range is going to be Q3 minus Q1, and you don't have to worry about the real limits for this. So we're going to say Q3 is 14 and Q1 is 10. So it's going to be 14 minus 10 equals 4. And the semi-interquartile range is just that number divided by 2. So 4 divided by 2 is in fact 2. Look how easy that was. Now, there are some pros and cons of the interquartile range and the semi-interquartile range. So the pros of it relative to the range itself is that it's not influenced by outliers that way, right? Because we're not taking people who are way out on the edges. We're leaving out the top 25% and the bottom 25%, and that's where the outliers will be if they're in there at all. And another thing about it, it includes only the scores that are mostly in the middle. It's the 50% of scores that are right in the middle of the distribution. And so it's a more stable measure of central tendency in that regard. So that's good. But the cons about it is it's only still determined by 2 numbers. And it still doesn't describe the actual distance between all the scores in a distribution. And that's what we really want to do, right? We don't care about just how far apart two numbers are. I butchered that, but you guys know what I meant. We don't care about how far apart two numbers are. We care about how far apart all the numbers are from one another. And that's what we need to actually come up with a better measure for. And so another problem with it too is that it still underestimates the population range, right? And that's a killer because it's even worse, right? Because you don't even have the highest and the lowest number person in the data set. So you really can't even get close to what the actual population range is if you're using the interquartile range or the semi-interquartile range. So that brings us to the two ones that we really love in psychology. We love variance, and even more than variance, we love standard deviation, okay? So these things are the most common and most important measures of variability, particularly standard deviation. So what standard deviation is, it's a measure of the standard. That's an important word. That's why it's called standard deviation. So it's a measure of the standard or average distance from the mean. And it's used to describe whether scores are clustered closely around the mean or whether they're scattered around. So to the degree to which it's a big number, that's not really good because that's telling you the scores on average are pretty far from the mean. All things considered, you want a nice small standard deviation if at all possible. An important thing to know, and I'm going to show you guys this in a little bit, is that the calculations of these things differ based on whether we're talking about the population or we're talking about a sample, okay? And so variance is a necessary companion concept to standard deviation, but they are not the same thing. So what do we know about the variance and the standard deviation? Well, we know that these measures actually take into account the average distance of each score from the mean of a distribution, and therefore they nicely describe the extent to which scores are clustered together or spread apart. That's the key thing about them. Every single score contributes to these things, not just the two on the top or the bottom, okay? And there are two highly related indexes or indices commonly used to measure variance, variance and standard deviation. And you're going to learn the formulas for one of them, but it's super easy because guess what? Standard deviation is just the square root of the variance. So if you learn the formula for variance, then you already know the formula for standard deviation because it's literally just the square root of it, okay? And there's a slight difference in how we calculate a variance and a standard deviation when we're talking about it being a population or it being a sample. And then another difference is we have these different formulas, and some of these things are definitional formulas and some of these things are computational formulas. And for those of you who were paying attention way back in lecture 3 where we learned statistical notation, I talked to you guys about one of the parts of this formula, and you should remember it if you come back to it in terms of things being definitional or computational for the sum of squares, and that's a big part of both of these formulas. And so all things considered, there's essentially 8 formulas you have to learn, but frankly, guess what? You can learn these things really easily if you just know one of them and you understand how they're all related. So you just have to put one of them in your brain and you can figure out how to get to the other 7 pretty easily. Or you could put all 8 of them in your brain if you've got all that kind of extra space. I don't, so maybe you're smarter than me. So go ahead and pull your formula sheet out. This should be on it. This is sort of just a screenshot of it. All this stuff here. These are the 8 formulas that you have to learn. And so what I want to do, let's just spend a second sort of looking at the differences between them, right? So all the ones over here, right? These are for variance. Okay, and then all the ones over here are for standard deviation. And so let's just look at the variance formulas really quickly, right? So what we notice is that n is always, the big N is always down here. So that's one difference between the sample and the population formulas. It's big N when we're doing a population, and it's not just little n down here when we're doing a sample, it's n minus 1. So that's the main one of the main differences. The other main difference in terms of just, let's go from the two definitional formulas. Well, we're going from having this thing, which is called rho, by the way. So rho is the variance because it's squared. So rho squared is the variance, and that basically gives you the population variance too. That's very important. That's why it's important in the first place, right? And then this S squared, that is the sample variance. And so those are the things that we use to denote those. And so that's the definitional formulas, and I'm going to talk to you about what it means to say they're definitional. They literally tell you exactly what you need to do to get it. But then we have these other formulas, right? These computational formulas for both the population variance and for the sample variance. And we use those because they're quicker and they just sort of help us get there in a much faster way than the definitional formulas do. So you need to know all of them for the exam or for your homework. You're going to have to learn all of them and how they all work. And so we're basically going to teach them all to you. Now, again, if you know the formulas for variance, right, it's pretty easy to get the formulas for standard deviation because they're literally just the square root of all those things. This thing here is the square root of that, and so forth all the way down, okay? So we don't need to worry about this side so much in terms of understanding and learning the formulas. Let's just focus over here, okay? So how do we come up with these formulas? And I'm gonna help you guys help me figure out how do we derive these things in the first place and understand this conceptually. So this is where things get really important. So if you're not paying a lot of attention and you're just sort of coasting through the lecture now's the time to sort of drink some coffee or whatever it is that you need to do so that you can focus, because this is where a lot of the heavy conceptual lifting for the early part of the course comes into play. So we're going to derive the formula for the population variance and the population standard deviation. And so we're going to get the population variance, right, and the population standard deviation. And we're going to do the definitional formulas, okay? I think that's what we said, okay? So first of all, we should ask, if we want to figure out how different each score is from the mean, well, why don't we just figure that out, right? We could get each score and subtract it from the mean and then just add those all together. That seems pretty easy to do, right? And so let's say we have this set of scores and everybody's got a 7 here. So if everybody's got a 7, then the average is clearly 7. And so we can say, well, for that person, 7 minus 7 is 0. 7 minus 7 is 0 for this group, for this person. 7 minus 7 is 0 for that person, and so forth and so on. And then when we get down to the bottom, we could add all those together and divide it by the number of scores. So it's going to be 0 divided by 4, and that is in fact 0. What that 0 down here means, right, is that we say we took the average, so we took each score minus the mean and added them all together and then divided it by the number of scores. If we did that, right, we would get 0. And that would basically be saying that there's no variability here. By saying no variability, what we mean is all the scores are the same. And that's true here, correct? All those scores are the same, so there is no variability, and that's exactly right. So this would be correct because there is no variability amongst these data. Now, we have this data. And for these scores, right, the mean of these is 7, right? So if you actually pulled out the average, let's do it. Let's pop the calculator up. So we got 10 plus 8 plus 6 plus 4 is 28, divided by 4 is 7, okay? And so the mean of that is 7, so we can take each score, and we can say 10 minus 7 equals 3, okay? And then we could say 8 minus 7 equals 1, and then 6 minus 7 equals 1. And finally, 4 minus 7 is negative 3. And if we added that stuff all together, it would also equal 0, right? Because we got a positive 3 and a negative 3 and then a negative 1 and a positive 1. And if we add those all together, we also end up with 0. And again, what that 0 means by saying you have a variance of 0 for a set of scores, that's saying, essentially, write this down, saying that the variance is 0 means that all the scores are the same or that you have no variability. Well, is that true here? It's true over here, right? Because all the scores are the same, but we get the exact same thing if we do that. And this is just one of the properties of the mean. Remember, we talked about the mean being a balance point. Well, what the mean is doing, it's balancing these numbers, right? It's basically saying, okay, well, we got to find a magic number that sort of gives 3 points to this one and negative 3 points to that one, and then 1 point to this one and negative 1 to that one. That's literally the balancing that the mean does. Okay, and so we didn't go to that much in the lecture about the mean, but this is sort of a good place where you guys can see it. Okay, and so again, we're saying that there's no variability amongst these numbers, and that's just crazy, right? Because these numbers are not the same. So this is not correct because there is variability here. So we can't just get the difference from the mean and then add them all together as a measure of the spread of these things, because it's not correct. It doesn't work statistically. What does work statistically, though? Well, one of the things we could do is we could square all of those differences, right? And we could see if that helps, right? And so we could say each score minus the mean squared. So for the first thing, we can say 7 minus 7 squared is 0. 7 minus 7 squared is 0, and so forth and so on, all the way down to the bottom. And if we did that, right, and then we got the average of all of those, right, what it would basically be saying is that 0 divided by 4 equals 0. And again, saying 0 is your variance is the same thing as saying you have no variability here or your numbers are all the same. And that is in fact correct, right? Because again, there's no variability here. So we get the same thing whether we squared those numbers or we didn't square them in this particular case when it was a constant. Now remember when we did this a minute ago, right? We just took each score and subtracted the mean of 7 from all of them, and it gave us something that wasn't 0, right? And so that wasn't correct. We can just do it, but now we can actually take those things and square them. So if we did 10 minus 7, that's equals to 3, and then we squared that, and that gave us 9. We could do that for each one of these scores as well. So 8 minus 7 is 1, and we square that to end up with 1. We can say 6 minus 7 squared equals 1. I'm sorry, yeah, 6 minus 7 is negative 1, and then when we square that, we get 1. And then 4 minus 7 is negative 3, but we square that and we get that negative 3. We square it and we get 9. Okay, and you can already see, right, what that squaring did, basically. It took these numbers that were negative and essentially canceled these out. And it sort of put them all on the same side of the ledger. And so when we do that now, we basically have to say, okay, well, let's average all that together. That's going to be 20 divided by 4 equals 5. And that's actually incorrect. So you guys take that and fix that because that's not supposed to be 0. I animated that incorrectly. This should say, if you're writing it at home even, go ahead and write 20 minus 20, sorry, it should just be 20 divided by 4 equals 5. And so I'll fix that on the slides for next year's class, but guess what? You guys get to have that mistake in there because I'm not starting all the way over. Okay. So, variance and standard deviation. Variance begins with this idea that we're going to find the difference of each score from the mean. And the basic idea with the variance is to get the differences and sum them together and divide by n to get an average idea of what those differences are. But this won't work unless we square those differences, right? Because again, some scores are going to be higher than the mean, some are going to be lower. So some of those scores are going to be negative, and the negative scores will cancel out the positive scores and just give you 0 at the end. So we have to square them so that that doesn't become a problem anymore. And that puts everybody on the same side of the ledger. Now, that brings us to the definition of the variance, literally what it is. It is the average squared distance of every score from the mean. So if you actually look at our formula, like that tells you a set of commands, you guys can probably write this in summation notation, right? It's the average squared distance of each score from the mean. So if you started at the back here, you would say, okay, I got to get each score, so x minus the mean, and then I need to square those things, right? Because it's the squared distance. And then I need to get the average of them, okay? And so that formula works out exactly how we said. In fact, hopefully you were writing that down as we were doing it, but if you didn't, pause the video and sort of write it down and work it backwards to see that this definition right here literally tells you exactly how to get the variance. Easy peasy. Now, the thing with the variances is they're in these weird squared units, and it's hard to interpret what they mean, right? So I could say someone has 4.8 squared friends, you know, and that's not terribly useful. We have to get this thing back into some metric that we can use, right? But one of the reasons we do like variances from an interpretational standpoint is they're useful for samples because they actually do produce unbiased statistics. And second, variances can be added together. So we can take the variance for one set of scores, and then we can add that to the variance from another set of scores. And this becomes really, really, really important down the road when we're trying to do a lot of these statistics. Now, otherwise, we want to get rid of it, okay? So it's good for those two things. But otherwise, we don't want those squares that we had to put in the formula. And so then we basically fix that problem of these things being squared by using the square root to get that, and that gives us the formula for standard deviation. And it sounds complicated, right? But the thing you have to do is just get the square root of the variance, and then you have it. So let's look at these formulas for it. So I pulled these out. These are screenshots of your formula sheet that you should have at home in front of you right now. And so we talked about how we get the population variance conceptually, right? So we defined the population variance and we sort of walked through the math in terms of how we got it, right? So let's look at it and see this top part of the formula. These are the definitional formulas, right, for both of them. So what this says is for the definitional formula for the population variance, because it's rho squared, RHO is how you spelled rho, by the way. What we do is we take each score minus the mean, we square those and then add them all together. And then we take whatever number that is and we divide it by n. and that gives us the variance. Well, if we wanted to turn the population variance into the population standard deviation, all we have to do is simply get the square root, okay? Now, we can get the sample variance the same way, right? Except there's a couple of differences. So look at these two formulas and go ahead and take a second and think about what's the difference between them. And I can see at least three things, and hopefully you can too. One of them is because we're going from a population to a sample, the symbol changes for the thing that we're using. It's now using the sample mean instead of a population mean, but it's still telling you to do the exact same thing. It's take each score, subtract the sample mean from it, and square them, and then add them all together. And then that brings us to the second difference, which is once you do that, you don't divide it by n, and you don't even divide it by little n, okay? You're going to divide it by n minus 1 for a very important reason that we'll cover in a second, okay? And so that's the second difference. And the third difference is the nomenclature for it, right? And so the nomenclature is no longer rho squared because rho squared is referring to a population variance. When we're talking about the sample variance, it's s squared. So again, those are your three differences, okay? Now, once we have the sample variance, how do we get the sample standard deviation? Do we have to do anything crazy? No. Essentially, all we have to do is get the square root of it, right? And so again, I've already just walked you through how to get 4 of these formulas just if you know one of them. So basically, if you learn the formula for population variance and you learn that, oh, well, all I have to do to go from a population formula to a sample formula is turn rho into S, turn mu into M, and then turn n into n minus 1, then you can get to all of these formulas in the exact same way. Cool beans, right? I think that's pretty exciting. And there's all the stuff that I said was different. So I should have popped that stuff up earlier, but you can see that those are 2 of the differences, right? You still have this third difference that's way out here. Sorry about that. So let's take a second and recap things here, okay? When we're going to define variance and standard deviation, step 1 is to determine the deviation of each score. Because remember, what variance is literally, what it literally means is the average squared distance of each score from the mean. So it's first thing first, you got to get the deviation of the mean, right? So a deviation score is going to be the score minus the mean, okay? Step 2 is we have to find the sum of those deviations to use as the basis to get the average, okay? And that is pretty easy as well. So we don't want to do that because that doesn't work, right? If we just added those things together, it wouldn't help us because they're all going to sum to 0. So the 2 problems, the things all add up to 0 because mean is a balancing point. And if the sum is if the sum is always 0, then mean deviation will always be 0. Okay, if we try to do that, and of course, again, that's not helpful for us. And so we need that new strategy of doing what? We got to remove those negative deviations. And the way that we do that in a linear fashion is by squaring all the deviation scores. And then we sum the squared deviations. And the sum of those squared deviation scores is called sum of squares. This is a very special thing in statistics. So put this in your brain and learn it right now. It's very important. So the sum of squares is short for the sum of squared deviations from the mean. And because we don't want to say that all the time, we just call it sum of squares, or SS. And it's very important that you learn that concept right now. Okay? And then, so step 3 is we're basically going to average those squared deviations. Once we get those things, we are going to average them all together. Okay, and so, I didn't pop this up, but what you should see is that the sum of squares equals each score minus the population mean, if you're doing it for the population, square it, and that's the sum of squares, right? Because you're not dividing it by anything yet, just to get the sum of squares. That's the top part of our formula for variance, okay? And so, yeah, that's right there. Now, again, we're going to get the average of those things, right? So the sum of squares divided by the thing on the bottom, which is going to be either n or n minus 1, depending on whether it's a sample formula or a population formula. The mean squared deviation, right, is known as variance, okay? And now, right now at this point, variability is measured in these squared units that I talked about because we put those squares up there. And so, okay, that's fine. And we can deal with that by saying that population variance equals the mean or the average square deviation of the scores from the population mean, okay? And that's pretty much all you have to do to sort of understand it conceptually, okay? And it's important that you understand this at a very deep level in terms of how these things sort of got there and why we use them and why they matter. Step 4 in defining variance and standard deviation. Well, again, we want to get a measure of the standard distance, right? So again, we don't want that squared units. We got to basically get rid of that. And so the way that we take that out is by getting the standard deviation. So what the standard deviation is the standard distance of each score from the mean. And so again, while the variance measures, it's a good measure because it does give you the average squared distance, and then we can do these cool things like add them together in ways that we can't do even with standard deviation. That's not quite our goal. We want to basically get this standard distance, and so we have to adjust for that by basically taking all those squares out by getting the square root of the variance. And so again, standard deviation is very simple. It's simply the square root of the variance. Now, population standard deviation, it tells you how far on average any given score is away from the population mean. Pretty simple. So again, that was the recap of all of that stuff, but let's look at it in picture form for those of you who like pictures like me, right? So I gave you a set of scores, okay? So one of the things you can do, you can start here. You can say, okay, well, we're going to, let's see, how does this work? So we're going to get each deviation and we can add the deviations and compute the average, and that's not good because basically that's going to always give us 0. So we have to do something different. We got to get those deviation scores, right? And rather than just adding them and getting the average, we got to square them first. And once we square them, that's going to get the average of them, right? So we have to get the average of those squared deviations. So you divide it by n if you were doing the population standard deviation, or sorry, population variance, and n minus 1 if you're doing the sample variance. And then you have to take the square root of that if you want to get the standard deviation. And that's fairly straightforward. Now, let's do some practice, okay? So I'm going to walk through this very slowly so you guys can do it at home with me. Let's find the standard deviation for the following distribution of scores. So again, assume they represent a sample. So remember the differences between a sample and the population formulas, right? We have m in the formula instead of mu, and down on the bottom, instead of dividing by n, big N, we're going to divide by little n minus 1. And remember also that the s is no longer rho squared that we're solving for, it's s squared. So those are the 3 big differences. And we're going to use the definitional formula to find the standard deviation. And I'm going to explain to you why we don't like using the definitional formulas, because it takes a long time. So the first thing we do, I gave you a set of scores, okay? So we got this set of scores, and then we figured out that the mean is 4. And what I want you to do if you're using the definitional formula, remember, definitional formula says first things first, you have to get the score minus the mean, and then you have to square what that number was. So for the first one, the score minus the mean is 4. So 4 minus 1, and you can write the whole thing out if you want, but 4 minus 1 is what? Sorry, nope, we're doing that backwards. Say it again and get it right this time, guys. Say it with me. It's going to be 1, because it's the score, minus the mean. So 1 minus 4 is negative 3. And then we have to square that, but we'll get to that in a second. The second, we're going to go all the way down here. So we're going to have 4 subtracted from 6. So it's going to be 6 minus 4 is 2. For the third one, it's going to be 9 minus 4. For the fourth one, it's going to be 0 minus 4, which will be negative 4. And then later on, we're going to have 4 minus 4 equals 0. And again, if we add those all together, what are we going to get? We're going to get 0, right? So here we have 7 positive scores, and then over here we have 7 negative scores, and that one equals 0. So we can't just get those deviations and add them together because it's always going to equal 0. That's literally what the mean's job is. The mean is to balance all these numbers, right? It's the number that will balance all those numbers so that you end up with 0. By definition, that's what the mean is supposed to do. Okay? But if we square all those things, that helps us get everybody on the same side of the ledger. And so if we do that, we get a negative 3 times negative 3 is 9, and 2 squared is 4, 5 squared is 25, 4 squared, negative 4 squared is 16, and 0 squared is that. And so again, the top part of our formula, again, check it out. We have this special thing, right? So we're doing this, and this n minus 1, I didn't say this earlier, but it has a special name in statistics too. When you're taking n minus 1, it's called the degrees of freedom. And I'll explain what degrees of freedom are another time. Because it gets really important when we get to doing statistical tests. So you'll learn a lot more about what that means later. But just know that DF, if you see SS over DF, that's like saying, oh, that's the standard deviation, right? Because remember, we have to get the square root of all these things. So if you take the sum of squares divided by the degrees of freedom, or all that stuff that we just calculated, because we're going to add that all up in a second here, and divide by n minus 1, and then get the square root of it, don't forget to get the square root of it, that gives you the sample standard deviation. So let's see if that works, right? So we got the sum of squares that equals all of this stuff, and that is 54, okay? That's easy to go. And there should be an equal sign between here. Sum of squares equals all of that, but that's fine. You guys can know that's what I mean. And so the sample standard deviation is basically going to equal the square root of 54 times 54 divided by 4. So if you add all those up, you get 54. And then we just divide that by n minus 1. There's 1, 2, 3, 4, 5 scores. So we're going to divide it by 4 because it's n minus 1. And that gives us 3.67. And we're super excited about that now, aren't we? I think we are. So now we know how to get both the population and sample variance and the population and sample standard deviation using those definitional formulas. Now, the definitional formulas are fine, right? We can sort of use those, but they are cumbersome and they take a lot of time and there's a lot of places to make mistakes, right? If you mess up one of those deviation scores or if you don't square something right, then it messes up the entire thing. So there's lots of places where you can go wrong. And it just takes more time. So right now we just did this with something that had 5 numbers. But what happens if you have 500 numbers? Do you really want to go through and calculate, you know, the difference of each one from the mean and then have to square all those things? It's like 1,000 things that you have to figure out before you can even do the real part of the math to solve the question. So we don't want to do that. That's stupid, and we're not going to be stupid in this class, okay? So we have these computational formulas, okay? So we have to get the mean to solve all those things anyway, right? And then we have to get each scores and we have to square them, do all that, and it just takes a lot of time. And we don't want to waste all that time. And it would be nice if there was a shortcut that didn't require to do that, and I'm actually going to show you that there is. We have a whole separate set of formulas, because on that formula sheet, remember I showed you that there were 4 of the definitional formulas, but there's also 4 computational formulas. And so we're going to go ahead and learn those. And we can see that in the top part of the computational formulas. And this makes our life so much easier, okay? So again, I've now highlighted the computational formulas for each one of these. And right now, you guys should all be able to read these, right? You did it actually when we first did the lecture, when you learned all the statistical nomenclature. I showed you how to calculate the top part for both of these, right? I had you do this and I had you do this. And if you don't believe me, go back and look at that lecture in your notes. You actually calculated the sum of squares, and I told you that's what they were. And so again, these things are always going to equal sum of squares. So this stuff here, this top part, pretty much has to equal the top part of this, right? So you basically put an equal sign and write that out. They're equivalent things. So, and I showed you that when we figured that out, you know, how to speak the Greek. But now I'm going to show you in a different way, right? I want you to see it in practice and why it matters that they're the same thing. So again, read this to me and tell me what it says, right? This should say, well, we had to get we had to square each score and add them all together, right? So we squared each score and then add them all together. And from that, we're going to subtract each score, right? So we're going to go through now and note this is actually the total score, and then we're going to square it, and then we divide that by n. Okay, so that's the difference, right? So again, we took for this thing here, you read that by saying take each score, square it, and then add them all together. And then this thing, right, because that's in the parentheses, this says add all the scores together and then square that total. And then we're going to divide that by n. And then that basically gives us the population variance formula, because it's still just n down on the bottom. Okay, and so that's the only difference between how you get from so you need to learn the computational formula. You need to learn population variance for both formulas, and then you can figure out the other 6 if you know these 2, essentially. Okay. Because again, to go from the population variance to population standard deviation, you just get the square root. And then to go from the population variance to the sample variance, you make those same changes we made before, except down here, it's still just little n. So you have you change the whole top out to match this, except it's just little n, and then it's n minus 1, and then s squared. Okay, so these formulas all sort of flow directly out of one another in a very meaningful, straightforward way. Okay. So, variance, again, it equals the sum of the squared deviations divided by the number of scores. And the sum of squares, which again stands for the sum of squared deviations from the mean, is the sum of the squared deviations of all of those different scores from the mean. And there's 2 formulas for computing it, okay? And so we showed you this before, but now we're going to show it to you again because I want you to be very clear that these are different formulas that give you the exact same thing. Okay, that's why they're both in the top part of the formula. So again, for the definitional formula, what you do, and we've talked about this like 3 times now, you find each deviation score, right? So you get each score and you subtract the mean from it. After that, you square each deviation score, and then you add them all together. Well, for the computational formula, what do you have to do? That first part, it says square each score and sum the squared scores together. Then you find the sum of the scores, square it, and divide by n, and then you subtract the second thing from the first thing that I just said a second ago. And so let's look at the formulas and see if that makes sense, right? This thing literally says take each score, subtract the mean from it, and square it, and then add them together. That's what all those words right there mean, right? Over here, this says square each score and sum the squared scores. So square each score and then add them all together. And then you're going to subtract the second part from the first part. So you're going to subtract what from it? You're going to subtract the sum of the scores, right? So we're just going to get the sum of the scores, square it, and then divide that by n. So that's all of that stuff right there. And these formulas are exactly the same. They're equivalent to one another, which is why we call this the definitional formula and we call this the computational formula. Because again, you'd have to calculate like 1,000 things if you had 1,000 things in a data set. You'd have to calculate 1,000 things times 2 because you have to square them all to get that. Whereas for this, there's only 2 things you have to calculate. You just have to square each score and add them all together. So I guess you have to do that first 1,000. But then you save a lot of time doing it this way because all you have to do is get the sum of those scores and square it. So to get the computational formulas, you simply just swap out the top part of that formula for variance standard deviation. You just swap the top part out for the comparable formula here. And it's pretty easy to do. So again, we just swap that top part out up here for this part right here, and those formulas are exactly the same. Now, again, take notes because here's a place where students go wrong every single year. Every year I ask, hey, what is the formula for population variance? I want to make you write out one of the 8 formulas on the exam. And what they always do, they make mistakes because they're not paying attention to things. So again, sum of squares. Some people think, oh, well, sum of squares means square all the numbers and add them together. No, that's not what it means. Don't be stupid. What sum of squares means, you have to remember what the whole definition is. Sum of squares means sum of squared deviations from the mean. So literally, that means take each score, subtract the mean from it, and square it. It is not the same thing as this. So SS is not that, okay? And then some people will actually make this mistake too, right? Well, this is not sums of squares, right? It's not the sum of the squared deviations from the mean. This basically says take each score, add them all together, and then square that thing. Well, that's not the same thing as this either. These 2 things are what sums of squares are. So don't make that mistake, and certainly don't make this mistake. Hopefully you guys are, past that by now, but don't make the mistake of saying that this thing is equal to this thing. This says square all the scores and then add them together. This says add all the scores together and then square it, okay? Again, you'd be surprised when I ask students to do this on the exam every year. About 5 or 6 students completely botch this because they're not paying attention. And now I can say, you clearly didn't pay attention during the lecture because I made a really big deal about not making that mistake. Okay? So, population variance, we got these final formulas, right? So we basically end up swapping things out, and I've sort of said that a lot, so I'm not going to go into it too much. You guys can read it if you want. Just remember population variance has rho squared, and then we swap that out for S. So sample variance is S squared, and then when we get the standard deviation, we just get rid of the squared because it's no longer in there. So we go to just rho for the population standard deviation and just S for the sample standard deviation. So let's do another example, right? Because you guys like doing extra practice. We're going to find the population standard deviation using the computational formula. And this time I was nice enough to throw the computational formula on there for you. And if you're just looking at it, it tells you, well, you need to get the sum of the squared scores, and then you need to sum all the scores together and then square that number. So let's go ahead and do all of that right now and then see if we can figure out what the population standard deviation is for this set of data. Okay, so we got to square all the numbers first, right? So 6 squared is 36, 10 squared is 100, 4 squared is 16, 4 squared is 16, 6 squared is 36. You should be writing these all down if you're not. 7 squared is 49, 11 squared is 121, 7 squared is 49, 3 squared is 9, 11 squared is 121, 6 squared is 36, and 12 squared is 144. And then we need to add all that stuff together. So I just went ahead and animated all of that, but I gave you guys enough time to do it with me. So hopefully you're right here where I'm at now. And we need to add all these things together, right? So we have 87 over here, and then we add all those together over there, we get 733. And if you don't believe me, you can stop and add it up for yourself, but I'm pretty sure it's right. So now we just have to take all that stuff, we have to plug it into our formula. And so if we're going to do that, you guys should be able to read this. We need to get the square root of the sum of the squared x's, right? We squared all of them. So that's going to be 733 minus the sum of all the x's added together and then squared. So 87 squared, we're going to divide that by 12 because we have 12 scores. And then we're going to divide all of that by 12 and then get the square root of all of it. Whew, that's a lot of work, but we can do it. So if we plug all that into our formulas, you're going to get 733 minus 87 squared divided by 12, and then divide that by 12 should equal 2.92. Okay, and let's do the math together. So I'm going to pull out a calculator to show you guys the order of operations, right? So first thing you need to do is get 87 times 87. Let's see, can we change that? 87 times 87 is that number, okay? And we need to take that number, we have to divide it by 12. That is the right thing there, yep, divided by 12. And that is 630.75, right? So all of this stuff in this parentheses is 630.75. And now we have to take that number and subtract it from 733. So 630.75, let's see if we remember that in like 2 seconds. 733 minus 630.75 equals 102.25. So that gives us everything in this set of parentheses, this second set. And so now we have to take all of that and divide it by n, right? Because we now have all the sums of squares up here. We have to divide it by n now. And so we're going to take that number and we're going to divide it by 12. And that should give us 8.52 is the variance. But then we have to get the standard deviation. So we have to get the square root to turn it into that. So all we should have to do, I believe, is hit this little square root button. And it is 2.919, which you will round up to 2.92. See, I was right. Okay. So let's talk about the characteristics of the variance, because just like the mean, it has these sort of weird mathematical properties that are sort of rules that I want you guys to know and understand at a very deep level. So the first thing is that changing the value of any single score changes the variance, okay? So just like the mean, if I had a set of scores and I just sort of changed one of them to something different, the mean would change. Well, if I changed it to something else, the variance would also change, right? So changing any single score changes your variability, and it changes the estimates of the variance and the standard deviation. Unlike the mean though, right? The mean had this rule where anything I did to all the numbers in terms of addition or subtracting, if I did the same thing to every score, that would change the mean. But that does not work for the variance, okay? So the variance does not work. If you basically add 5 to all the numbers, that doesn't change the variance. The variance stays the same as it was before because because the mean moved, right? And remember, we're talking about differences from the mean. So the mean moves and the variance doesn't when you're doing addition and subtracting. So that first rule that we learned about the mean is not true with respect to the variance when it comes to adding and subtracting constants to all the scores. But it is true. So again, I actually just said this. This is because every score moves the same amount, but the mean moves too, so the differences from the means are maintained. But that rule does apply for when we are multiplying or dividing scores by a constant. So if we multiply every score by 2, then the variance increases by 2. So the first rule doesn't work for the variance, and the second rule does. So let's do a learning check. These are both true and false questions, so let's see if they're true or false. The first one says that the computational and definitional formulas for sum of squares sometimes give different results. Well, that should be blatantly false, right? Because we said that they always give you the same thing just because they're equivalent formulas, so that's got to be false, I would think. And second, if all the scores in a data set are the same, then the standard deviation should be equal to 1. Well, I'll give you guys a second to think about what that means. Okay, I would say that should also be false, right? Because if all the scores have a variability of 1, that means that's their average difference from the mean. If all the scores are the same, they should have a variance of 0, and the standard deviation should naturally be 0 because it's the square root of that. So I would say both of these should be false, and they both are. Look at that. The second one is the standard deviation measures what? Does it measure the sum of the square deviation scores? No, it can't be that, right? Because the sum of the square deviation scores is just going to be 0. The standard distance of a score from the mean, well, that seems like a decent answer, but let's read the rest of them and make sure that they're not better, because don't just stop once you find one you like. Read them all, because I'm a tricky guy when it comes to exams. I sometimes throw things in there that are just a little wrong or sound a lot right, and that's not the answer. So C says the average deviation of a score from the mean. Well, that's like saying that's the same problem, right? If we just add all the scores together, they're going to sum to 0, and then I get the average of that, that's still going to be 0, so it's not C or A, clearly. And then finally, we have the average square distance of a score from the mean. Well, that sounds intriguing. That could be it, right? But that's not it, because if you remember correctly, that is the formula for the definitional formula for something else. The average square distance of a score from the mean is the measure of the variance, right? So don't confuse the two, right? The answer is going to be B. It is the standard distance of a score from the mean, and I hope you guys nailed that one. So that's what it should be. So measuring variance and standard deviation for a sample. So again, the goal of inferential statistics is that we want to draw conclusions about a population based on something that we know about the sample. And it's not just based on the sample, but it's based on limited information from a sample, right? A sample is never as good as the population, and you can only have samples that are better or worse than other samples. Now, we can draw samples from the population, and we've made a big deal about having to have representative samples, but samples are always going to differ from the population, right? They're never going to exactly match it. One, samples will have less variability, right? Because you don't have everybody in it. And computing the variance and standard deviation in the same way for a population as we do for a sample will give us these biased estimates of these population values. And that's the reason why when we're doing the sample formulas, we use n-1 instead of n. So again, you can see the population of heights of adults in America here. And so here's what this sort of looks like, right? We could basically say, here's the population variability. We can take that and we can draw out some samples. And you can see that if we took a bunch of people, let's say we're going to have a sample of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. The variability of our sample is smaller than the variability of our population, right? Because we just took a bunch of random people. And that's pretty much going to be true regardless of what we do, because we're never really going to be so lucky to get the person that's way out here and the person that's way out here, right? So that's problematic for a reason. So again, notice that our sample does not have as much variability as our population does. Therefore, we say that the sample variance and the sample standard deviation, they're biased estimates. That's what we call biased, right? They don't give you the population parameter exactly. The population mean formula actually is not biased. It actually does give you back the population mean. So that's why we use the sample mean as a good one. And we use that n-1 in the formulas for the sample standard deviation and the sample variance to show that we know that we're understanding them, right? So that we're underestimating them, rather. So we know that this isn't exactly right. So we basically say we have to account for these things called degrees of freedom. Remember I said that earlier, that n-1 is a special thing too. And so this is basically just a way of us accounting for the fact that we know we don't have everybody and we're underestimating this thing. So we give ourselves a little bit of wiggle room to be wrong. The sample variance as an unbiased statistic. So again, when we talk about something being an unbiased estimate of a population parameter, what we mean by that is that the average value of that statistic is equal to the parameter. And we're going to go into this a lot in the next lecture, I believe. So if you don't understand what that means now, and you shouldn't have to really, it's going to become very important down the line. So we could get all of the possible variances of like infinite amounts of samples from that thing. And the average value uses all of them at a particular size. And theoretically, if it's unbiased, what you should get if you got the average of all possible samples, you should get back what the population thing is. And that works for the mean, and it doesn't work for the sample standard deviation. It works for the population standard deviation, though, because you have everybody. So again, we correct the sample standard deviation formula for by dividing by n-1 to get this unbiased estimate, at least what we call it unbiased. But if you don't do that n-1 down on the bottom, you're not correcting for it. So that n-1 is to help us correct for the bias that's in that formula. And when we talk about something being a biased estimate of a population parameter, what that means is that it systematically overestimates or underestimates the population parameter, and typically just going to be that it underestimates it. So that's not also terribly important, but again, I want you to sort of understand that the n-1 thing is important for that reason, because it helps us get rid of the bias in our parameters. So now we have the sample variability and degrees of freedom. So again, when we're talking about population variance, right? If we know the mean of the population, we can get those deviations from the known mean. The thing, though, when we're talking about a sample variance as an estimate of the population variance, Again, we don't know what the population mean is. And so what the problem with that is that we have a sample, and that sample mean is restricting our variability. Because again, remember, it's each score minus the mean squared. Well, if the mean isn't exactly what the mean is supposed to be, because it's not the population mean and we don't know that, that's where this bias comes from. Okay? And so then degrees of freedom, again, the number of scores in a sample that are independent and free to vary, that's what degrees of freedom are. And the way I always like to tell people this is like, think about it like this. If I say I know what the mean of something is supposed to be, right? So if I know that you guys have to have an 80 average, so let's say there's 3 people in the class, and I know that their average was an 80 on the exam, okay? So I could say, okay, well, I know somebody got a 70, and I know that somebody got a 90. Well, if I know what those 2 people got, that third person can't just have any score. The first 2 people can have whatever score they want, right? Whatever score the data sort of telling me it is. But once I know what 2 of those 3 scores are, and I know the mean, that third score has to be a particular thing. And what we do, the way we sort of account for that statistically is that's why we say n-1 is the degrees of freedom, the number of scores that are free to vary. Well, 2 of those scores were free to vary. They could be 70, they could be 90, they could have been 160. But either way it went, right? That third score had to be the number that balanced those things all out. And so that number isn't free to be whatever it wants if you already know what the means are. So that's what degrees of freedom is all about. And that's the bottom part of all of our formulas for variance and for standard deviation. So let's do another learning check here. All right, so we have a sample that of 4 scores, and it has a sum of squares of 24. So what's the variance? And so this should be pretty easy. We know that the variance is always going to be what? It's going to be the sum of squares divided by the degrees of freedom, right? Because we're talking about a sample, right? We've got a sample of scores. So it's going to be 24 divided by 3, or is it 24 divided by 4? The variance should be divided by 8. So this was actually done with respect to a population, right? Because theoretically, I would have told you, had this been a sample and you're calculating the sample variance, you're going to divide it by n-1. So I disagree with that answer. I think the book got that wrong, but we'll just say it's 8 for the sake of the example. Say I told you that we were calculating it as a population instead of a sample. Again, a sample of 4 scores has a variance of 8. If each of these scores was multiplied by 3, what would the new variance be? Well, remember, we learned 2 rules about the variability and the variance, right? The variance is not affected by addition and subtraction, but it is affected by multiplication and division of all the scores. And so if I multiplied all of the scores by 3, and the variance was 8 before, it's going to be 8 times 3 now, which should be 24. And I believe that is the end of the lecture, and we'll see you next time.